Okay, this video here is going to be about the geometry of the dot product, the assumption being that you know how to calculate a dot product, and now we're going to try to give some geometric meaning to it. Okay, so to start off, we're going to draw two vectors, called them A and B. They meet at a common initial point, and the angle that they form is going to be called theta. And we're going to take these two vectors and we're going to go ahead and enclose them to make a triangle. So we have a triangle here, and notice the vectors. If we start here at the initial point, we go out to B, there's the terminal point of B, and then the new vector starts and goes this way, ends here. So both A minus B and A end right here at this point of the triangle. And we know from our geometric definition of vector addition that if we add this vector and this vector, we should get A, the resulting vector, and B plus A minus B. The B's are going to combine to make 0, and we're just going to have A, which is what we should. So this is the triangle that we're going to work with. And now we're going to bring up something that from trigonometry called the law of cosines. And the law of cosines is just a generalization of the Pythagorean theorem. Okay, Pythagorean theorem only works with the right triangle. The law of cosines works with any triangle. Okay? The angle that we've labeled theta, that's going to play sort of the role of the right angle in the Pythagorean theorem, and hence the opposite side, the vector that's A minus B, is going to play the role of the hypotenuse. And so here, if we read off the law of cosines, it's going to say that side, or the length of that side across from the angle theta, its squared, is going to equal, well, there's one leg and there's the other leg, the two legs that form theta. We're going to square those and add them. So if we stop right about here, right, that looks just like the Pythagorean theorem, but now we have to make an adjustment because we don't have a right angle. And what comes after that is minus 2 times the length of A times the length of B times the cosine of theta, the angle between A and B. Okay? And I'm going to use this to show, to get a geometric meaning for what the dot product means. Okay? Just a reminder, here are some properties we talked about in the dot product video, properties of the dot product, and we're going to use a few of these pretty extensively, especially 1, 2, and 3, as we try to go through here. So if you need to, you can back up the video and come look at these, or you could just pause it now and jot down the first 3, since we're going to use those quite a bit. So I'm going to start with the left-hand side of the law of cosines. Left-hand side, the square of that side opposite the theta, the A minus B squared. Okay? And then I'm going to use that property 1 that says that is equal to whatever the vector is that we're looking at its magnitude dotted with itself. Okay? And then I can use the property 3, which looks like a distributive property. Okay? So we'll treat A minus B right, as the vector. Okay? That is being multiplied by A and by minus B. Okay, so we have it dotted with A, and then subtract the vector A minus B dotted with B, and then we'll again use this property of looks like the distributive property. Also, the way it was defined in those list of properties, we distribute through what's in front of the first vector, and so you could think about, really moving this A over here, A dot A minus B, to get these two terms, right? So we have A dot A minus B dot A minus, and then we did the dots here, kept some parentheses around to make sure we don't make a sign error, and all I'm going to do on the next slide is just distribute that negative sign through. Notice the first and the fourth terms are something dotted with itself, so we can go back and use property 1, right? And we have the magnitude of A squared, the magnitude of B squared there. The two middle terms, we look at them, we say, oh, wait a minute, they're the same thing. They're just written differently, but It's the commutative property that allows us to write them the same, which I'll just write explicitly there, and then once notice I have two of them, I'll gather them together, and I'll end up with this term. So from beginning to end, we're saying that that the magnitude of the side of the triangle opposite the angle theta, its length squared, is equal to, right, the length of the vector A squared, one of the other sides of the triangle, minus 2 times A dot B, plus the length of B squared. So how is that going to help us? No. That right there in red is the original statement of the law of cosines from a little while back. Okay, and then here in blue, okay, is the other expression that we just calculated. It's also equal to A minus B, that magnitude squared. So since they're both equal to that, we can take the right-hand sides of both of these expressions and set them equal to each other using transitivity. And so we end up with this. I took the blue, that's on now the left-hand side of this equation, and then the right-hand side of the red equation is the right-hand side of this new equation. And as I look at that and look at ways to simplify, notice that I've got these magnitudes of A squared and magnitudes of B squared on both sides. So if I subtract those away, okay, I suddenly have a much simpler looking equation, and also it jumps out at me that I have a factor of -2 in both, so I can divide through by that, and it says that the dot product, okay, another way to define it, other than the way we did last time with the pairing up of corresponding entries so that we do multiplication and then we add all of those products up, the dot product is also equal to the magnitude of A times the magnitude of B times the cosine of theta. And that theta is the angle formed by A and B. So there are two ways to express this result that we've come up with. You know, the first one listed here is exactly what we had on the last slide, but the second one is to go ahead and solve for cosine, right? And then you have that the cosine of theta is equal to that dot product divided by the product of the two magnitudes, the magnitude of A times the magnitude of B. And this is really interesting from a geometric perspective because it tells us that when we have two vectors, there is some sort of relationship between their dot product, their magnitudes, and the angle between them. And they're all three of those ideas are boiled into either one. Either way you write this expression. Really kind of neat and unexpected result. It's a new term now, new probably to most of you, the term orthogonal or orthogonality. It says two non-zero vectors are orthogonal if the angle between them is pi/2 radians. Okay? So the vectors have to be non-zero, okay? Because the zero vector is kind of not that exciting a case. Okay, and though I do note here, right, that the zero vector is considered to be orthogonal to every vector. So you might think of this as the word perpendicular, which we certainly have used in geometry and calculus before, and this is just another word for that. I think usually in a mathematical context, if we say orthogonal, we're allowing ourselves to be in more than just two-dimensional geometric space. We could be in higher dimensional spaces, and if we have this property, then we say orthogonality. Now it follows just from this definition and from the work we did before, okay, that these two statements are true. That if the two vectors A and B are orthogonal, then their dot product is 0. And taking that if-then statement and just turning it around, taking the then part and making it the if part, and the if part the then part, it says if the dot product is 0, then A and B are orthogonal. It's easy enough to prove either one of these statements just using the little bit that we did in this lesson today. So I'll leave you with that. You enjoy, and see you next time.